This will be the last video on section 6.8, and that's the video on indeterminate forms and L'Hopital's rule. I'll be considering indeterminate powers in this video. Now, assume that I want to find the limit of f of x to the power of g of x as x tends to a. Then we could have some possibilities that make it difficult for us to know what the limit would be. One of those possibilities are stated from number 1 to 3. Imagine that the limit of f of x as x tends to a is 0, and the same is for g of x. Then in this case, this limit is going to be 0 to the power of 0. This gives me an indeterminate form of type 0 to the power of 0. Now, why is this a problem? Well, notice that 0 to the power of anything k is equal to 0. And any number k to the power of 0 is equal to 1. So now, if we have 0 to the power of 0, is it going to be equal to 1 or is it going to be equal to 0? That is a problem, and that is why 0 to the power of 0 is indeterminate. Next, imagine that the limit of f of x as x tends to a is infinity, while the limit of g of x as x tends to a is 0. We have indeterminate form of type 0 infinity to the power of 0. Now, why is this a problem? Similarly, as we have that infinity to the power of any number k is equal to infinity, and any number k to the power of 0 is equal to 1. So infinity to the power of 0, is it going to be equal to infinity or is it going to be equal to 1? Well, we don't know. That is why that is indeterminate. And finally, the same also holds for number 3, because this x is going towards 1. So if it's going towards 1, it's basically bigger than 1. Assume it's going towards 1 from the right. So if it's going towards 1 from the right, maybe 1.5, 1 point anything, any number bigger than 1 to the power of infinity is equal to infinity. But 1 to the power of anything, k, is equal to 1. So 1 to the power of infinity, is it going to be equal to 1 or is it going to be equal to infinity? We do not know, and that is why it's indeterminate, an indeterminate form. So when we have indeterminate forms of powers, what do we do? Well, the easiest way to solve this is by taking the natural log of the power. So if we let y equal to f of x, we can take the natural log of y so that the powers become products, and then we can now find the limit by one of the methods that we have studied already. Another way to do this is by noting that x is the same thing as exponential natural log of x. So my f of x, for instance, or let me write this as y. My y is something as exponential natural log of y. So if I have y to be a function raised to another power, I can write it this way. I think it's usually easier to use this form instead of the other one, but anyone you are okay with, you should get the same thing. So if we have that, we arrive at an indeterminate form of products, and then we know how to find indeterminate form of products, and we employ that method to solve problem. We are just going to look at a few examples involving this kind of scenario. Now imagine that you're asked to find the limit of 1 plus sine of 4x to the power of cotangent of x as x tends towards 0 from the right. What is this going to be? Well, we know that as x tends towards 0 from the right, my 1 plus sine 4x tends towards 0, or 1, sorry, because sine 0 is 0. So this is going to tend towards 1 plus 0. Tends towards 1 plus 0, which is 1. Cotangent of x tends towards infinity. Cotangent of x tends towards infinity. Why? Because cotangent, cot x is something as 1 over x, or 1 over tan x. Tan 0 is 0, so 1 over 0 is infinity. That is why as x tends towards 0 from the right, cotangent of x tends towards infinity. So now this tells me that this is an indeterminate form of type 1 to the power of infinity. Now, how do we solve this? Well, we say we let y to be equal to 1 plus sine of 4x to the power of cotangent of x. And then take the natural log of both sides. If we take the natural log of this, we get that natural log of y is equal to the natural log of 1 plus sine 4x to the power of cotangent of x. And by law of log, this power comes down to be cot x natural log of 1 plus sine 4x. Now, we can find the limit of the natural log of y. How do we find that limit? Well, a limit as x tends towards zero from the right of the natural log of y is equal to the limit as x tends to 0 from the right of cotangent of x multiplied by the natural log of 1 plus sine 4x. Now, how do I solve this? Well, I know this here, the limit here is infinity. The limit here is going to be 1, as we saw over here, and the natural log of 1 is 0. So this tells me that I'm going to have indeterminate form of 0 times infinity. How do we do this? Recall that usually we write this as, instead of product, we write it as a fraction. So that is what I'm going to do here. So this will be limit as x tends to infinity. I'll just leave the natural log above since it's more complicated. 4x here, all over 1 over cot x. But what is 1 over cot x? 1 over cotangent of x is the same thing as 1 over tan x, which is just tan x. So this tells me that the limit here is equal to limit as x tends towards 0 from the right of the natural log of 1 plus sine 4x divided by tan x. And now we can find what this limit is. I know that the limit of what I have above is going to be 0 because the natural log of 1 is 0. Limit of tan x as x tends to 0 is also 0. So I'm going to have indeterminate form of type 0 over 0. And so I can apply L'Hopital's rule to this. L'Hopital's rule says that the limit is just going to be equal to the limit of their derivative. If I differentiate the natural log of 1 plus sine 4x, I'm going to get 4 cosine of 4x, verify that this is correct on your own, divided by 1 plus sine 4x. and this is divided by the derivative of tan x is secant squared of x. Now, if I take the limit of this as x tends towards 0, I'm going to get cosine of 4. This is going to give me 0. And I'm going to get 1 plus 0. Cosine of 4x will be 1. This will be 4. The limit of cosine of 4x as x tends to 0 is 1. All over 1 plus limit of sine 4x as x tends to 0 is 0. All divided by limit of secant squared as x tends to 0 is 1. So if you simplify this, you're going to get 4. So that tells me, therefore, that the limit of the natural log of y is equal to 4. But I'm not really looking for the limit of the natural log of y. I'm looking for the limit of y. So how do I do this? Well, I just have to recall one thing. I just have to recall that if I want to find the limit of the y itself, I'll just take the natural log of exponential of both sides. So this would be equal to 0 plus. For me to find my y, I will exponentiate both sides. So I'm going to have exponential limit as x tends to 0 plus of the natural log of y is equal to exponential 4. Now this limit can come down because the exponential function is continuous, and I get limit as x tends to 0 plus of exponential natural log of y. This is equal to exponential 4. But what is exponential natural log of y? The two functions are inverses of the other, so this is just going to be y. So this will be the limit of y as x tends towards 0 from the right, which is equal to, what was my y? Well, look here, I let my y to be this whole thing, so I'm just going to change y to that whole thing, and that is limit as x tends towards 0 from the right of 1 plus sine 4x to the power of cotangent of x, and this thing here is equal to 4. So this is my limit, and you've seen how I'm able to use some other techniques I've learned to find what this is. Actually, I've taken the space I'm supposed to solve problem 2, so I'm going to solve that last. First, let's try to look at problem 3. That one is a little bit more easier. Here, if you compute this limit directly, you get an indeterminate form of type infinity raised to power 0. Because if you take limit of x, you're going to get just infinity, and take limit of 1 over x, you're going to get 0 for x going towards infinity. So we can apply the same method here, taking the natural log. But since we know that if we let our y equal to x to the power of 1 over x, then y is same thing as exponential natural log of y. So I'm just going to write this to be equal to the limit as x tends towards infinity of this whole thing here is exponential natural log of that 1 over x. And by law of log, this is going to be limit as x tends towards infinity of exponential. This power is going to come down, so I have 1 over x multiplied by this. So what is that going to give to me? Well, I can take this limit above. If I take the limit to the power, exponential function is continuous, I'm going to get this will be equal to e limit as s tends towards infinity of 1 over x natural log of x. But one way to see this here is the same thing as exponential limit as s tends towards infinity. 1 over x times ln of x is same thing as ln of x over x. And then if I take the limit of this, I'm going to get somewhere indeterminate form of type infinity over infinity, because ln of x goes to infinity as s goes to infinity, the same also with x. So now I can apply my L'Hopital's rule by identifying this indeterminate form. I can apply my L'Hopital's rule to get that this will be exponential limit as s goes towards infinity of the derivative of what I have here. If I differentiate ln of s, I get 1 over x divided by 1, derivative of x. And if I take the limit of this, I'm just going to get 0. So this will be equal to exponential, the limit of this whole thing is 0, and my exponential 0 is equal to 1. That tells me that, in conclusion, that the limit of x tends towards infinity of x to the power of 1 over x is equal to 1. Now notice that I really didn't need to go back taking exponential, because from the onset here I just used the concept or the idea that x to the power of 1 over x is something as exponential natural log of x to the power of 1 over x. So that's the idea I used. If I did it the other way around, maybe by letting my y equal to x raised to the power 1 over x, and then taking the natural log of y, and then finding the limit of the natural log of y, then at the end of the day, I need to go back exponentiating both sides to get what my y is. But I just did that from the onset here, and that is acceptable. So anyone you are using would be nice if only you understand why it works and use it consistently. Finally, let me talk about the question that was skipped, and that question is the one here, number 2. Number 2 is limit of x to the power of x as s goes to 0 from the right. So I'm just going to solve that here. Limit of as s goes towards 0 from the right of x to the power of x. Now this is going to give me, I'll just be fast with it, this is going to give me indeterminate form of 0 to the power of 0, 0 to the power of 0. So what can we do about this? Well, maybe we'll do it the other way around. Let's let y to be equal to x to the power of x. This means that natural log of y is equal to the natural log of x to the power of x, which is something as x this. So the limit as x tends towards 0 from the right of the natural log of y is equal to the limit as s goes to 0 from the right of x ln of x. I think we found the limit of x ln of x before. Yes, I know we did that by noting that this is an indeterminate form of the type 0 times infinity, and the limit of this is just going to give you 0. Find this. I think you should be able to do that. The indeterminate form is like this, and the limit is equal to 0. Please don't skip the steps. If you're doing this in an exam or homework, you need to show it. I just need to finish this video before it becomes longer than I expect. So since the limit as s goes towards 0 from the right of the natural log of y is equal to 0, to find what my y is, I'm going to exponentiate both sides. If I exponentiate this side, I can pass that, bring down my limit. Or let me write it out. I hope the step I'm skipping doesn't cause confusion here. Natural log of y is equal to exponential 0 is 1. This implies that my limit can come down. So the limit as s tends to 0 from the right of exponential natural log of y, which is just the same thing as the limit as s tends towards infinity of y, exponential natural log of y is y, is equal to 1. But what was my y? My y is s raised to the power x. That tells me, in conclusion, that the limit of my y, which is x to the power of x, as s goes to 0 from the right, is equal to 1. And that is that. So we've seen various techniques that we can use to compute limits, and I hope you remember these techniques. This brings us to the end of chapter 6, which deals with inverse functions. In the next video, I'm supposed to give you like some general problems based on all the things we've done in this chapter. I'll do that during the week of your first midterm. However, I'll just move forward to the next chapter, which is chapter 7, techniques of integration.